Welcome back to Simple Harmonic Motion. We're going to take another look at this particular type of motion, but we're going to slice it a little bit differently. We're going to look at it from an energy perspective. If you remember, previously we took over a semester to work our way through motion, right? Kinematics, and then forces, and then energy. We're doing all that in kind of a fast-forward way. So we took one or two lessons to go through kinematics. Today we're going to take a closer look at energy. Let's get started. On the screen you see two examples of simple harmonic motion. These are mechanisms by which we can visualize simple harmonic motion in a sinusoidal fashion. Okay, I think you're familiar with the example on the left. I showed that in the previous lesson. The one on the right I didn't actually cover. I want to cover it quickly. We can actually represent circular motion in a sinusoidal fashion as well. If you look at that mechanism on the right, we're using lamps to project a shadow of the object on the turntable. Okay. And I think if you look at that for a minute, you can see how the back and forth motion of that object, of that little ball on the turntable, can produce also a sinusoidal motion. So circular motion can also be represented sinusoidally, and the motion graphs for an object moving in a circle can be, we'll have the similar graphs to those of the mass on a spring or a pendulum. All right, let's take a look at these from an energy perspective. Let's go to the next screen. Here are the kinematics graphs from previously. Okay, we talked about how they're connected, how as you go down the graphs, right? To go down the graphs is the same way as you go down the graphs of a linear motion kinematics graph, and that is to look at the slope, right? The slope of the velocity time graph is the acceleration time graph. The slope of the position time graph is the velocity time graph. The fancy math way of doing that is to take the derivative, okay, to take the derivative of the function that describes that graph. We are going to use those graphs today, okay, as a baseline for seeing how kinetic and potential and total energy behave in a simple harmonic motion system. All right, let's go to the next screen. We're going to call on your knowledge from last year. If you remember, the elastic potential energy, okay, of an object goes as 1/2 kx squared. Okay, so this is a formula that you had previously, all right, from linear motion. We're going to use that today to show you how the energy behaves for simple harmonic motion. I'm actually looking at a pendulum. Okay, that was the simplest to sketch. So I've sketched underneath the position time graph, I've sketched the position of the pendulum at different points. Okay, we start here at the equilibrium point, right? And then the pendulum swings to the right to its extreme and then to the left. Okay. So in this example, I guess to the right, right? This is not typically how we do this, but in this case, to the right is negative, right? Because I have negative position here. All right. Since the potential energy depends on position, right? Displacement x squared. Okay. The graph for potential energy is going to look very similar. The only difference is if you have a quantity squared, that quantity can never be negative. So what's going to happen here for our graph is it's going to look like this. It's going to follow the same shape as the position time graph, right? Like that. That wasn't a very good sketch. It's going to basically go like this, okay? But now watch what happens here on the second bump. It's going to go up again, like that. So I was going to go up, okay? And that's because if you go over here to the position time graph, right, this section here, okay, that gets flipped up to the top because all those negative values get squared and become positive. So at the same points in time, position and potential energy are doing the same things. They're peaking at the same time. It's just that all the potential energy peaks are positive. All right, I think you're going to see a similar pattern on kinetic energy. All right. If you remember kinetic energy, okay, and this again is drawing on your knowledge from previously. Okay, kinetic energy depends on the velocity. Obviously, it depends on mass as well, but we're interested in the velocity aspect because we know what that graph looks like. The mass for a given system is going to stay the same, right? So the thing that's varying is the velocity time graph. So you're going to see the exact same thing happen here. You're going to see the kinetic energy be a maximum when the velocity is a maximum, and the minimums will be the same too. It's just those negative values, they're going to get flipped around again, right? So if I want to sketch that, that's going to look like this. So this part will look the same here, but then I'm going to get flipped up, right? It's just going to get all these are going to be positive again like that. Okay, they should all be the same and do that very well. I'm going to pause and try to sketch it a little more nicely for you. Okay, you see a cleaned up version. What we're going to do now is we're going to take the kinetic energy and potential energy and look at them at the same time. All right, so let's look at that on the next screen. Let's see, right here. Okay, so I've sketched them underneath each other so you can see how they line up. Now remember, in our particular example, the position went as the sign, right? We started at the equilibrium position. So if the position goes as the time, then the potential energy is going to go as the sine squared, right? And the kinetic energy is going to go as the cosine squared. So that's what you see here, okay? So what I want to do now is on the graph to the right, I'm going to put both of these, okay, in a different color, but on the same graph so you can see how they correspond to one another at different points in time. Okay, you see both graphs together, and in this case, I guess I should mark these. That would be the EPE, right? And in light blue, you see the KE. Okay. In other words, when one's a maximum, the other one's a minimum, right? When the pendulum's at its extreme, when the mass on the spring is stretched to its fullest extent, it's momentarily not moving, right? Maximum potential energy, but zero kinetic energy, and vice versa. At the equilibrium position, it's moving the fastest, but the spring is unstretched and the pendulum's hanging straight down. So you can see how those two correspond. Hopefully it makes sense to you that the total energy in the system at any given time is still constant, right? Conservation of energy. Okay? And so the total energy graph would look something like this. It would be a flat line, right, where at each point that would be incorrect. It would be right like this. Okay? Like so. If you take a look at this point, say right here, okay, all of the, let's do a dotted line. Right at that point, all of the energy is potential energy. So the total energy is the maximum potential energy. And then at a short while later, right here, all the energy is kinetic. Right? So that's why that red line is at the tops of those crests. What we'd like to do now is take a look at energy from a more mathematical perspective. We've looked at it graphically. Now we want to look at the equations that go along with these graphs. Let's go to the next screen. You'll see our basic expressions for kinetic and potential energy that we use today. What we're going to do is we're going to combine these current equations with some equations that you already have in your arsenal to derive and come up with some new equations that are specific to kinetic and potential energy in simple harmonic motion. Now, in your previous lesson, you got the following expression for velocity in terms of the displacement of the object from the equilibrium position. So it looked like this right here. Okay, square root, that thing. So we could substitute that into right there, okay, to derive a new expression for kinetic energy in terms of position and the angular frequency, right, that fat W, which is called omega. What I really want to work on is the expression on the right side, because I kind of threw that out just to kind of help you understand where the graph came from. But if you think about it, a pendulum doesn't have a spring constant, right? Remember that K stands for spring constant. So I really do need an expression for for potential energy that is more general, right, in terms of things that would apply to all simple harmonic motion systems like circular motion, masses on a spring, as well as pendulums. So I'm going to work on that. That's really what I'm after, is I want to work on that expression on the right side. But in order to do so, I'm actually going to first work a little bit on the left side. So I think you'll recognize that we've talked previously about this, but the maximum velocity occurs at the equilibrium position. Okay, and the equilibrium position is defined as x equals 0. So if you substitute that into this expression here, right, this whole thing goes away, and v ends up being plus or minus omega square root of x naught squared, right, which I think you'll see just comes out to omega x naught, right? So what we're going to do is we're going to take that and we're going to substitute it into here. And this is where we get a new expression for kinetic energy maximum, right? 1/2 m omega naught squared x naught squared. So now I have an expression for maximum kinetic energy. We can use that actually to derive an expression for potential energy by using the total energy. Remember that the total, okay, is always at any time the sum of the kinetic and the potential at that point. And so all we'll do is at this one position, right, when the object's swinging through the equilibrium, we know that the total energy is this, E total. We know that the max kinetic at that point is this new expression that we just found. And we know that the potential energy is 0. That means that the total energy at that point, okay, is equal to the maximum kinetic energy. Now think about what if we, let me clean that up. All right, a little bit cleaned up. Now think about, so this is when the pendulum is, if I just draw it here real quick, right, this is when the pendulum is, if I'm using the pendulum as an example, is right there at the center. But what happens when the pendulum swings to its extreme? Well, that's going to be a situation where the potential energy is going to be a maximum, right? And at that point, remember, the total energy is constant the whole time. So now we get an expression for the potential energy, okay, at least at its maximum. It's going to be equal to the same thing as the kinetic energy's maximum, like so, all right? And then if we wanted to get an expression for potential energy at any time, we could just substitute in the position function, which in this case was this right here, okay, sine omega t. Or we could do over here for the velocity, right? Velocity was a cosine function. We could substitute that into the kinetic energy to get the kinetic energy and the potential energy at any one time. But the reason I do all this is, again, to clarify what you're going to be given in the data packet. Okay, so let me highlight those right now. It's a little cluttered here, so let's go to the next screen. All right, you'll see, and I'm going to highlight, okay, I'm going to rectangularize those that you get on your data booklet, okay, in your data booklet, these here. These are the ones that they give you. Okay, they actually don't give you any potential energy functions, but if you know the kinetic and you know the max, you can subtract. You know the total. You can subtract the two to get the potential energy function. I did write for you the potential energy function in terms of position. Okay, and again, that might, if you substitute in the cosine, right, it might look something like this. And notice also that I wrote E sub p and E sub k because that's how IB likes to write it. But this might look something like this as well. Okay, you might write it in terms of sine and cosine. One last thing to look at, and that is the omega, what that might be. It's going to be different for different systems. I'm going to do one more screen. I'm going to just give to you what omega is for a mass on a spring and what it is for a pendulum. These two formulas you're about to see you do not get in your data booklet. On the next screen, you'll see the two expressions, okay, for the angular frequency of the pendulum, okay, where the L is going to be the length of the pendulum, right? This is acceleration due to gravity, okay, and then looking over here at the spring, this will be the mass that's on the end of the spring, and this will be the spring constant. Again, IB does not expect you to know these, okay? They would either give them to you, or they would help you to derive them. I don't think you'll have to derive them, though. But what you do want to look at is what this means for, say, the period of a pendulum or the period of a mass on a spring. What are the quantities that the period of an oscillating system depends on and what it doesn't. In other words, if I double the length of the string of the pendulum, does that make the period longer or shorter? If I have a stiffer spring, does that make the period longer or shorter? That's what you should be looking at in terms of these formulas, since IB does not expect you to memorize them. All right, there you have it. Energy in simple harmonic motion.